Hello everyone, it's June 29. Hard problem incoming. Let's do this. I did it before. I might have remembered how to do this. Might. Alice and Bob have an undirected graph of n nodes and 3 types of edges. 1. Traversed by Alice only. 2. Traversed by Bob only. And 3. Traversed by them both. Given an array edges, type UV represents the bidirectional edge of type between nodes U and I. U1 and VI. Find the maximum number of edges you can remove so that after removing the edges, the graph can still be fully traversed by both Alice and Bob. The graph is fully traversed by them if starting from any node, they can reach all other nodes. I do not remember this problem at all. Return the maximum number of edges you can remove, or return -1 if Alice and Bob cannot fully traverse the graph. So, this is the begin. Type 1 is Alice, so Alice and Bob is this, and this is both, right? And we want to remove maximum number of edges to keep them traversable. Remove maximum number. So if we remove, so in this case, it's fully connected, right? It's a fully connected graph, and we need to remove. And once we remove an edge, well, if we have this, right, you have an edge that both can traverse, and you have edge only one can traverse, so those can be gone, right? And yeah, this and this, right? Thank you. 1 1 1 1 3. Oh, you remove these two. So basically we need to see for Alice what edges are necessary for Alice, and or maybe can we think about this problem the other way by means of adding edges. What do you think? Adding edges. Adding edges. Well, if you think greedily, the edge that's shared by both is most likely the most important. You don't want to remove the edge shared by both, because that, yeah, if you have an edge that's shared by both, I think that will definitely be an advantage, right? So you keep those first, and you can have two what's that thing? Find and join. Join, find? Yeah. Union find. You can have two union find. One representing Alice, one representing Bob. And then you go with a union find, right? So you put them together. And after that, if you do union find, after you go through all the blue edges, and you will, decide. But the thing is, yeah, you do all the blue edges first, and after you do the blue edge, if before you add an edge, it's already like it's already connected, right? It's already connected. Then you don't need to add that edge because that edge is duplicated, right? Okay, so you go through all, so you find the necessary, like all the blue edges that's needed to keep everything connected, and then you start looking through for Alice, right? You look through the red edge, okay, and you try to see which one can make it, or which two or whatever, right, can make it all connect. How do you do that? Yeah, how do you do that? So you can again go through, but what you don't know, oh yeah, and if it's the red edge, it doesn't really, the red edge doesn't affect the green one. So you go through the red edge, you find the minimum you need to add, right? You find the minimum you can add. You find the minimum you can add, and then that's the number of edges you can remove for the red. And for the green, you do the same, right? You do the same. I don't know. Do you think this one will work? Alright, so I can try that. I can try union find, and then basically just add edges. It's hard to prove, right? It's hard to prove. But, I mean, you say it's hard to prove, but I think it's okay, right? You do the edge that both share, and you definitely want to keep, right, the minimum. And the thing is, maybe if you, you keep a different one, right? Instead of doing this edge, if you do another edge, you'll have the same effect, okay? You'll have the same, if it has the same effect, then it doesn't really matter which edge to keep, right? For the blue one, it doesn't really matter which edge to keep. If you keep edge A or keep edge B, it reaches the same result, right? So it doesn't really matter. And from that connectedness, you add a red edge. It doesn't really matter. I think this one will work, but I will have to write a union find in Java, which I find that I do not have any intention to do that in Java because, oh Lord, union find in Java. What do I need? I don't even remember how to do union find. Oh, it's hard to find directly that way. Okay, so what I need is, alright, no. There we go. What I need, a list. Range n. DSU, disjoint set union. I think I can do in Java. I forgot how this one is done. Okay, that's fine. That is okay. What do I need? We need a copy. Let's try this. Let's try to maybe we can do it in Java. Alright, so basically we say class DSU, right? And we'll say DSU int parents rank, right? DSU number this dot parent equals new int, and this dot rank equals a new int. Okay. We'll do that. We need to. Oh, I didn't know this. Huh. This is an easy way. Alright, so we just say for int I0 I smaller than I plus plus, this dot parent I is equal to I. Alright, so that's the setup. Okay, then we just say find. Find is going to be int find private public find x, right? We say int p equal to this dot parent. Wait, hold on, no. Let me give him while this dot parent x is not equal to x, this dot parent x shall equal to find this dot parent x. I think that's the way to do it, right? And at the end return this dot parent x. If it's not equal to, return, yep. Next is public a void union x and int y. Okay. I say int px equal to find x, int py find y. Okay. If px is not equal to py, if these two are not the same, if the two are not the same, then we say if this dot rank px is larger than this dot rank py. If that's the case, then this dot parent py shall equal to this dot px, right? If rank is smaller than that, parent of this equal to this. Yeah, parent elif this dot rank py is larger than this dot rank px, this dot parent px shall equal to py, else then this dot rank px plus plus and this dot parent py px. Right? If rank is smaller than that, if rank is larger than that, otherwise x or rank this. Yep. That's it. So that's DSU. Okay, so now we have DSU. Let's put this one in. Alright, so now all we need to do is go through this, find all the edges that belongs to Alice. Okay, find all the edges that belongs to Bob, and for the remaining edges, so we add it to it. So we need to have int res 0 and list integer, Alice, new array list, list integer. Now I think I can do both at the same time. Right? I think I can do both at the same time. So we need to say DSU, Alice, because a new DSU. Oh, how about n? Well, we have n nodes, right? We have n nodes. Yeah, and then we need them to all be connected. We need them all be connected. Okay, so with the DSU Bob. For int e of edges. I think type UV, right? Type UV. So type we have 1, 2, 3. 3 is together, 1 is Alice. If E0 is equal to 1, Alice only. So we're gonna union them too. I do need, so if not equal, so union successful, so return true. Otherwise, so I should return false, right? Which means this is gonna be a Boolean value. So I'm gonna union these two. So if Alice.union E1 E2. But the problem of this is an edge it might need to be for Alice. Yeah, that's the problem. That is the problem. So I do need to separate Alice and Bob and have those done separately. Okay, so it's Alice Bob. I also need list integer Alice edges and list integer Bob edges. Okay, and Alice edge only, we don't do this. Okay, so we basically just said Alice edges.add e. We just add it. Else, if e0 is equal to 2, we say Bob edges. E. Else, right? It's shared edge. Always try to add. Yeah, this is, I don't know if it's gonna be right, but I think it is because it gives Bob a chance. When I say if, oh, now we have Alice and Bob. If one of them is a duplicate, but for the other is important, I think we'll keep it, right? I think we'll keep it. And which means for Alice, we probably don't need that anymore, but for Bob, it might be important. Yeah, let's just try this, right? So if Alice.union E0, E1, E2, if it's true, all right, if it is true, then we don't do anything, all right? But if it's false, we'll only remove it if both, right? So if not this and not Bob.union E1, E2, right? Which means this edge is not needed for both. Then we remove it. If it's required by one of them, right? If it's required by one of them, but not by the other, then we'll do. But essentially, because these are all shared edges, so it won't be. Yeah, it won't be. Okay, it won't be. But I do have to do both. And essentially, I think I can just do, right? I can just do this. Else if, right? So if I do this, else if 1 is true, or 1 is true, at least one of them is, no, if both are true, my bad. If both are false, yeah, it was right, the original logic is right. If both are false, which means for both it's already connected, then we do res plus plus. This is so we can remove it, right? So we can say the current edge is not needed. Not needed. So we go through all of them. So first round, and then we'll go through Alice alone. So we'll do basically the same thing. Int E of Alice edges, right? If not Alice.union E1 E2, then res plus plus. Okay, and then for int E Bob edges, if not Bob.union E1 E2 res plus plus. These are all just added edges. At the end, we need to go through Alice and go through Bob to see how many different, right? How many different parents they have. It should be only one. So we can say a set of integer Alice Alice cliques, right? Alice parent new hash set, and we do a set integer Bob parent. Here I don't even need that. How many? 10 to the 5th. And I can just do 10 to the 5th. I don't need a set. Yeah, set usually takes more time. So I can say int Alice parent. Not even int. All I need is a Boolean value. Boolean this new Boolean n. Right? That's that. We can copy this exact same thing, and we do Bob. Then we just say for int v equal to 0, v smaller than n, v plus plus. Int Alice parent equal to Alice dot find v. Int Bob parent and Bob dot find v. If Alice parent or no, if it doesn't exist, or yeah, if there is a repeat. No, what we want to find is at the end how many distinct parents there are. Yeah, we just need to see. It should be only one parent. Exactly. So, yep. So I think you just say int Alice parent is -1. Bob parent is -1. Okay, so we go through. We do this. Alice parent, Bob parent. If Alice parent is not equal to AP and Alice parent is not equal to -1, or Bob parent is not equal to BP and Bob parent is not equal to -1. Right, maybe I need one more into this. Then we'll return -1. That is an impossible case. Otherwise, either they're equal or it's a -1. Right, and then we just say Alice parent equal to AP, Bob parent equal to BP. Right, we just go through the whole thing and we'll return res. Alright. We need 41. I don't know, let's try. Time limit exceeded. All right, I need to see if the DSU got wrong. Oh, it's not while. It's a if. Okay, it's not a while. Index out of bound. Really? Type UV, right? Oh, I had to do +1. Okay. I don't want to change the code here. I can just do this. +1, +1. Right? And then these are all fine. This is all fine. And here, it's just going to be from 1 to smaller, you go to this. Alright, let's try this. Interesting. So we add these, right? And then, so I remove this. I'll remove this, but I need to add this. So it should be the 2. Interesting. Alice Bob edges. Looks fine to me. Probably here. Alright, we need to print something now just to take a look. What is the current thing? So what we're gonna do is system.out print line array.toString. I'll say Alice.parent. That's what I need to know. And this is gonna be Bob. That's what I need to know. Plus, I need to know the current res. That's good, right? That's good. And Alice is all to 1. Bob 1, 2, 3, 3. Parent 1 and 1, 2. Yeah. Bob, what happened to Bob? What the hell happened to Bob? What happened to Bob? Oh, I know what happened to Bob. I know what happened to Bob. It's a short circuit, so one of them didn't run. Okay, so what am I gonna do? So what we're gonna do is boolean unnecessary, like a duplicate, right? Alice need edge, go to alice.union e1 2, right? Boolean Bob need edge union e1 right. Should I say if Alice doesn't need edge and Bob doesn't need edge. Okay. Okay. Okay, try this. My bad, I forgot to do. Here should be +1, and here is okay. Okay, that's good. Let's try both. No, I have 3 examples. Okay, looks to be solid. $15.79. Use union find. First, we handle all the type 3 edges that is shared by both Bob and Alice. We can remove any edges, any type 3 edges that is not necessary. Then we handle Alice's edges alone. Right, Alice's edges alone, removing any unnecessary. We do the same for Bob's edges. Finally, we check, right? Finally, we check if Alice or Bob's union contain more than one parent. Right. Technically, it's, I'll say, because union find, the runtime is like what? Akama. I'm up bound the Akama function. I don't know what it is. All right, let's see if union find gets accepted. It is union find, which will work, but based on the fact that I have 2 solutions in past, it pretty much means there is another solution. So I think this is probably union find. I don't know what the next one I did. Yes, union find. Very good, very good. Very good, very good. Turn it into a set. Yeah, that's fine. What's this one? This one's union find again. This one is to keep track of the components. 2 nodes need to be union. The number of total components must decrease by 1. So we just need to check the components. Oh yeah, this is. Yeah, that's, yep, makes sense. All right, so we're gonna do 2 as well. So components. Start components equal to n. Right. Number of distinct parents. Okay. So this will be this dot components minus minus. Right. When two nodes union, the number of parents decrease. Right? Because it's 2 distinct, so we decrease. Okay. So we will do the same thing, but with the same solution as solution 1, but with a more performant union find where we keep track of the number of components in the set. Also, we do not use extra space, right? Extra space, because we can simply loop through edges to twice to get Alice and Bob's own edges. So I do this, no need, go through this, no need. We're basically gonna just say if E0 is equal to 3. Do this. If not, we do that. I'm curious. Did I do this? It's fine. And we do the same edges. If E0 is equal to 1, that's Alice, right? And this else if E0 equal to 2, and Bob plus I don't need this part. Alice dot components is equal to 2, and Bob dot components is equal to 2. Yeah. Check components count. It has to be 2 because we have an extra parent 0. So I'm going to do this. That's all right. Yep. Pending. Faster. Okay, that was good. Done? All right. I'll see you guys tomorrow. Adios.